In this problem, we have a few resistors and 2 op amps in a circuit. In this case, the op amps are ideal, and they're set up to be voltage followers. This is important to know. It gives us information about what the op amp is supposed to be doing. In this case for U2, the op amp is taking a signal from V2 at its non-inverting input and reproducing that same signal, 3 volts, at its output, which happens to be connected to node VB. So node VB is equal to 3 volts. Let's look at U1. The task is the same. The input of 2 volts from V1 is going to be replicated at the output and connected to VC. Node VC is 2 volts. The next thing we'll do is use Ohm's law to calculate the current I1. Since we have node voltage VB and node voltage VC, we can use both of those. Three volts minus 2 volts over 1K will give us 1 over 1000, which gives us 1 milliamp. Now that we have current I1, let's move on to solving for node voltages VA and VD. To do this, we can make use of all 3 of these known values, Ohm's law and KCL. Using this convention, I'm going to create a KCL equation for node VB in order to solve for node VA. I'm going to show you how this looks, and then I'll explain why it works. The KCL equation at VB looks like this. We're going to have VA minus VB over 1K set equal to VB minus VC over 1K. Let's look at how this simplifies. And remember, hold off on plugging in the known values. We'll have VA minus VB equals VB minus VC. If we're solving for VA, we isolate that by adding VB to both sides. This gives us VA should be equal to 2VB minus VC. We were able to calculate node VA by doing KCL at VB because of one important connection. If you look at our calculation, there's an assumption that IR1 is equal to IR3. This is true, but I want to make sure you understand why this is true. At first glance, you might think that IR1 and IR3 are equal to each other because the resistors are in line and look to be in series. However, an important part of this question is understanding that these 2 resistors are not connected to each other in series. Let me show you why. Components connected in series must obey the following rules. They share one node. The shared node connects to nothing else. And the same current must flow through the components. In our case, rule number 2 is violated. Rule number 2 is violated because R1 and R3 don't share node VB exclusively. Notice that in rule 2, it mentions connections, not currents. So when we look at node VB for a series connection, we need to look for branches. I'm going to highlight the branches that are a part of node VB. This is 1 for R1. This is 2 for R3. But this is 3 for our inverting input of U2. So this is why this connection disqualifies a series. Although this branch exists, we were still able to set up our KCL at VB to ignore it and assume that IR1 and IR3 were equal to each other because our op amp is ideal. This tells us that even though this branch is here, there will never be a current flowing into the inverting input. Therefore, the current through R3 would have to equal I1. We're going to use that same theory to solve for node VD by doing KCL at VC. We're going to have the relationship that the current through R1 is equal to the current through R2. VB minus VC over 1K is equal to VC minus VD over 1K. The last value we need is the power of V1. We know that power is equal to conventional current times voltage. We have the voltage, but what's the current? Since our op amp is ideal, we know that there's no input current to the inverting or non-inverting input. So 2 volts times 0 amps should give us 0 watts.